Hey there, my name is Oliver and I'm a computer science student. I've been deeply interested in machine learning and artificial intelligence, especially large language models, which I'm currently focusing on in my bachelor's thesis. Since large language models and natural language processing are such important and fast-growing fields, I want to help make some of their core concepts more accessible. One of the most fundamental of these is embeddings, or word vectors, and that's what today's video is all about. So, why do we represent words as numbers? Well, one reason for this is because computers only know ones and zeros. So with ones and zeros, we, using binary representation, can represent integers. And if you'd like to learn more about this, I made a video in the past about binary numbers and how exactly that representation works. So I suggest you check that out if you're interested. And integers in this case are numbers like -5, 0, 1, 12. And when we have a word like car stored in a computer, we store this as a list of characters, so C, A, and R. And each of them has a representation, but we're not storing them as these letters in the computer. We are representing them through an integer. So for example, 6 for C, 7 for A, and 8 for R. This isn't exactly how they are stored. There's different numbers for these, but just for this representation, I'll show it like this. So in a computer, we will have the binary numbers 6, 7, and 8 written after each other to represent the word car. But this is not super helpful because we want to have words represented in computers, specifically because we care about the meaning and comparing meaning. So this is how stuff like text documents are stored, where their exact meaning is not important for the computer. But if we want to have the meaning be represented, then we need to work more with entire words, or actually tokens in this case. A token is something between a word and a character. Here you can see a tool for showing tokens and a sentence broken up into them. So here you can see that many words map to one token, but some don't, like this word indivisible, which is composed of 2 tokens. Now exactly what is a token and what isn't is defined by a tokenizer, this one specifically for ChatGPT 4.0. And then each of these tokens has a certain representation, and this is this integer that we talked about. Now here you can see this or these sentences that I just showed you, how they are represented in the computer as a list of numbers. Again, now here, instead of having a list of characters, we have the list of tokens. So in the case of car, for example, we would map it to the token 15. But now there is one problem. This does not give us as much information as it could. So for example, the word automobile is very similar in the meaning of car. And so for example, it could have a token like 14, but this doesn't mean that the token with the ID 16 is exactly as similar to car as the word automobile is to car. So we actually need a bit more information for us to be able to compare these words, as language is very complex. So what stores more than one number? Well, several numbers, and this is exactly what vectors are. They're a collection, or rather a list of different numbers. In this case, we have the number 0, 1, 0, 0. And this specifically is called a one-hot encoding. This means that exactly one entry here is 1 and the rest are zeros. And this can be considered equivalent to our case with just integers. So for example, we say this is the representation for car, and then the vector 1, 0, 0, 0 is our representation for automobiles. So this is just a different representation telling us when what belongs to what. So then how exactly does this help us with meaning? Well, these one-hot encodings are actually commonly used as entry points for better defining these vectors. So currently these are very sparse and have no semantic relationship, so no meaning, but these are entered into a neural network or a specific model that's responsible for improving these, and using data, these are trained to optimize them. So for example, for our representations, these might be then -1, 0, 3, 6, and then -1, 0, 4, 6. So they are still very close to one another because only this last value is different. But we also have a lot more factors that can differ. So for example, if we have automobiles, so the plural, maybe this -1 will be a 0. And then the same relationship can be described by turning this -1 into a 0. So from car, we get cars. So there is a lot more room for these vectors to differ. And so more meaning can be encoded. And exactly these are then considered our embeddings. Here we have an example of a two-dimensional case where we have the vectors king and queen, and also man and woman. In this case, king could be represented by a vector such as 2 and 5, because we go 2 to the right and 5 up for this vector representation. But what I wanted to highlight here is that once these vectors are encoded, their meaning is somewhat intuitive. So for example, in our representation, and this is just approximately, our vector king minus the vector for man plus the vector for woman would give us the vector for queen. So these numbers actually have the meaning for king and queen stored in it, because exactly this difference of this king being a woman means that the king is actually a queen. And this is exactly what makes these embeddings so powerful. They allow computers to work with this meaning and computationally use this in certain ways. So now we saw intuitively what these embeddings do, but now the question is, what can we do with these embeddings? Well, one thing we can do is semantic search. So we can find words that are similar to one another. For example, we can tell that the word king and queen are similar because they are somewhat in the same space. If we had another one, which would go somewhere here, we would know that this has a low similarity to these two. And we can calculate the distance between two embeddings, and this allows us to say how close different tokens are to one another. So for example, in this simulation here, you can see that the embedding sailing here is close to, for example, the embedding for sail to the top left here, or submarine, and less close to, for example, embedding for what we have back here, Kiev. Now this representation is in 3-dimensional space, but actually what it's representing is in 200-dimensional space. So it also is a bit harder to understand what's going on here. I just wanted to highlight that similar words are closer to one another. Another thing you can do is sentiment analysis. And this is, for example, telling whether the content of a message is positive or negative. And this can be used, for example, to identify hate speech in social media. This would look something like having an area in your graph and saying, yeah, this is all the positive emotions and this is all the negative emotions. This is maybe all the hate speech. It's a bit more complex than that, but essentially it allows you to computationally tell when something might be associated to a certain emotion or sentiment. Another thing which you can do is machine translation. This essentially allows you to put different words from different languages into this number representation. So we have this number representation and it's different from any language, from any grammar, from any alphabet. And so, for example, the same words from two different languages would be able to map in the same area, that you would be able to, using the exact embedding of these words in these languages, notice when they are similar. And with the help of that, find the word that is equivalent to the translated word, and doing this for entire sentences. One further relevant concept is that of context, because we have certain words, like for example bank, which might have several meanings. So we would have, for example, the river bank or the financial bank. And here, the exact representation of bank should not be the same for both of these because they have two different meanings. And so what is done is that the representation, so the embedding of the token river, would be used to improve the representation of bank. So it would influence it. And the same would be for financial and bank here. And they update each other in such a way that then these two are different exactly in a way that would explain their meaning in this context. This also brings us to attention, which essentially utilizes this context to improve the representations so that embeddings of related words influence each other. The same as the previous example we saw, as well as the words, for example, baseball bat and winged bat. That this word bat, so to say, has its attention on this word winged and thereby changes its own meaning. And exactly this attention mechanism is what has been so effective these last years in large language models like ChatGPT. It allows large language models to understand context and use it to improve their responses. If this helped you understand embeddings, check out my video where I explain how large language models like ChatGPT use tokens to generate text. Don't forget to like, subscribe, and drop a comment if there is a concept you'd like me to break down next. Thanks for watching.